we're going to get some numbers for this, okay? When you circle the ball every 4 seconds, we'll get a number. And then when we increase the angular and the linear velocity, right? Most of you, the vast majority of you, not everyone, but for the vast majority, including me, when I first thought about this question, which is bad because I designed the question, is I thought tension would increase, right? Now there's some intuition to that, right? Because we've looked at these kinds of situations before, right? It's going at this nice gentle speed, and I know you're not doing it with me, but you can imagine it's not tugging on my hand. The tension in the string is not very high. Now as I increase the speed, it starts to pull more, and I have to hold on to it harder, otherwise it's just going to fly off, right? So tension in the string, as I increase the speed, it's also increasing, okay? So let's have a look and see what happens to the maths, right? The very first thing I'm going to do, and most of you executed this just fine, is I'm going to take all of my constants and I'm going to throw them into here, okay? So we'll do vertically first, okay? So what do we got here? T cos pi on 6, which is root 3 on 2, right? Plus n cos pi on 4. You know enough about me to know I really like the conversation you're having. I mean, not everyone got to the same point where you were. Is that okay? Yeah. Great. It's okay. Where were we? Cos alpha. What's cos alpha? Cos pi on 4, it's 1 on root 2, right? Okay. Equals, now we know what the mass is, and gravity, that's, I should say times 9.8. Okay, so far so good. Let's tidy this up a little bit, okay? This is going to be, what's that, 19.6? 19.6, but I sort of want to clean this up a little bit, right? So I'm going to multiply through by 2 as well, okay? So what I'm going to get here is, that'll be root 3t. Multiply this by 2, you get root 2. Okay, so this is going to be 4 times that, which is, oh, I don't know, 19.6 plus 19.6, which is 30, 8.2? No, 9.2? 9.2. Of course it's 9.2. Okay, there you go. There's equation 1, which I get from vertical forces. Okay, horizontally, okay, I'm going to go here and I'm going to do exactly the same thing. I'll just save us a bit of time. When you multiply it out, you should get t plus this same factor because it's sine alpha, still 1 on root 2. And you're going to get, I think, 4 omega squared. Yeah? Was that all right? Okay, now in this particular case, right, I need to work out what omega is, right? 4 seconds, that's how long it takes to go how far? 1 revolution, which is 2 pi radians, right? And I put it in this order because omega is radians per second. Okay, so in part A, omega will be pi on 2 radians per second. All good? Okay, so when you throw that in, you square it, will get you pi squared on 4. 4 times pi squared on 4, pi squared. Yep. Okay, so yeah. Okay, so then what did we do at this point? What are we trying to do? We're trying to solve for tension, right? So you look at these two equations, right? You see that, well, this number is bigger than this. So I think you would do 1 minus 2. Yes? Save you a bit of time. Eventually you solve for t, and I think to 1 decimal place, you get 40.1 newtons. So far, so good. Okay. Now, when you go to part B, a lot of this is the same, but what changes? At what line do I have to adjust things? Line 1, line 2, line 3, line 4. This line doesn't work anymore, does it? Because it goes with this, which goes with this, right? But that's changed, okay? So instead of omega being pi on 2, when you crunch this in, I think you get 2 pi on 3 radians per second. Okay, so you're going to get something different on this right-hand side. When you do the same thing and you go ahead and solve, right, the tension in the string is, what is it? It's like 20-something? 29.6. 29.6? It's less. The tension in the string is less. How can the tension in the string be less, right? it seems to be pulling on me more the faster I make it spin. But of course, in this picture, there's something missing, isn't there? What's missing from this picture? What's missing is there's no ball. Because, well, frankly, I don't have a ball that's, you know, that's this big, okay? But what difference does the ball make, right? The ball is pushing, its reaction force is pushing in this direction, okay? Now, as this thing gets faster, right, you can now think of this as, think about how I said, oh, okay, you know, so it's pulling on my hand more, right? It's pulling further away. If I let go, it'll really fly, right? But if there's a ball there, the ball's pushing back, right? And because it's pushing more in that direction because it's going faster, the ball is also pushing back more, right? So therefore, the tension in the string drops because the reaction force increases. Does that make sense? It's a bit counterintuitive, right? But most of us, when we anticipated that it would increase, not decrease, is because we forgot that there's a ball there and it contributes its own force. And that force changes based on, you know, you push on a table, the harder you push on it, the harder it pushes back. Unless, of course, you know, you're really strong and it crumbles, but I'm not that strong. Okay. So, I picked out this example for two reasons. Because the hemisphere is tricky because the angle of the normal changes, as opposed to the cone, it's always the same, okay? So you need more information to solve it. But secondly, it gives you this really cool counterintuitive result. So I hope you learnt something as you got to this number and brain exploded, okay?